So today we're going to discuss rational exponents, in other words, exponents that happen to be fractions, because that's what rational means. And we've got a few properties in front of us. The first one, as we can see, is if we have some base term a raised to the 1 over n power, it becomes a root with what we call an index of n. This little thing inside the root sign within the little check mark thing is called an index. And if we have a to the 1/3, that's equal to the third root of a, or we call that the cubed root of a. If we have a to the 1/2 power, that's the square root of a. There's an implied 2 here. There's actually a 2, but it'll never be written. But that's a square root. Now, the index means how many times must you multiply a number by itself to get the number underneath the root. So for instance, in this problem, if I want to simplify the 64 to the 1/3 power, that's the same as the cubed root of 64. So in other words, what multiplied by itself 3 times get me 64, and I know that's just going to be the number 4. Likewise, if I have 32 to the 1/5 power, that's the same as the 5th root, my index is 5, of 32. And what do you multiply by itself 5 times to get 32? That's the number 2. Now, when we have numerators and denominators, not just the denominator is the index. So as you can see here, this denominator becomes the index. And this numerator can be the power of the base inside, or I can rewrite it if it makes it easier to do the problem, such that I have the denominator as my index of the base, and then that whole quantity is raised to the numerator's power. So we're going to simplify each of these examples, and what I try to do is I try to keep the number as small as possible so I know how to work with it. I don't blow it up too big. So you'll see in this first example, I have a numerator and denominator. My denominator is my index, so I have the cubed root of 27 to the 4th. Now my problem with this is 27 to the 4th is a huge number, and I don't want to deal with that because I don't know what that is. So if I take and say this is the cubed root of 27, and I take that whole term and raise it to the 4th, I know what the cubed root of 27 is. It's just 3. And I raise that to the 4th power, and 3 multiplied by itself 4 times gives me 81. Likewise, if I have a denominator of 4, that means my index is 4. So I have the 4th root of 16, and I'll take and cube that. The 4th root of 16 is 2. Cube 2, and I get 8. Finally, denominator of 2 means I have a square root of 4, and I'm going to raise that to the 5th power, which gives me 2, because that's the square root of 4, raised to the 5th, which is equal to 32. Now, we're going to take and change each of these from radical form, or from exponential form to radical form. And notice we have variables in this case, so it's going to be hard to find actual answers. So what we can do is we can do the following. We can say this is the same as denominator of 3, so that's the cube root of c to the 5th. Or we can write that as the cube root of c to the 5th power. Likewise, we'll notice in this case I have 12g to the 4/7. The question is 4/7 is attached to what? The 12, the g, or to both? Well, in this case it's only attached to the g because the 12 has an unwritten power of 1 on it. So this is 12, and then that's multiplied by the 7th root of g to the 4th. And then we're going to go from writing in radical form to exponential form. So here I have two radical terms, and I'm going to write that to an exponential power. So this is the base of 35. I take a look at the power that 35 was raised to, and it appears to be to the first power. And then my index is the denominator of my fraction. I see once again that 35 had an unwritten power of 1 on it. So that's 36 or 35 to the 1/6 power. Likewise, I look over at this next problem and I have A, and that has 15 to its power, and B has 40 to its power. But each of them are under the radical with an index of 5, and 5 becomes the denominator of my power because it's the index in both terms, since both terms have the fifth root as its index, and then I just reduce. So this is A to the third and B to the eighth. Now, I'm going to move on and talk about solving exponential equations. Let's say I have this equation. I have 5 to the x power equals 5 to the second power. Now, not meaning to insult anybody's intelligence or anything, but what do you think the answer is going to be? Well, if I have one number raised to a power and that same number raised to another power, in order to be equivalent, those two powers have got to be equal. So therefore, I can say here that x is equal to 2. And that's only the case if my two bases are going to be the same. So there's a little property that goes along with this. And the property states that if I have any base raised to the x power equaling any base raised to the y power, okay, that will only be equal if x is equal to y, or if the two powers are equal. So they give us an example: if 5 to the x is equal to 5 cubed, then x has got to equal 3, just like the problem we just did. So let's take a look at some applications of this. I've got a similar problem here. I've got 5 to the x is equal to 125. Now the problem is we can't really divide by 5 here because this is not a multiplication, so I can't undo it by division. So what I need to do is say, can I get these numbers into terms having the same base? Well, 125 is a power of 5. What power of 5 is that? It's the third power. So I have 5 to the x is equal to 5 to the third. Therefore, x has to equal 3. In this case, we have a fraction, and typically when we have fractions, we're talking about negative exponents. So I have 3 to the x is equal to 1 over, well, 243 has got to be 3 to some power. So let's think about what that is. I've got 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. I know this is 3, 9, 27, 81. 3 to the fifth is 243. So that's equal to 1 over 3 to the fifth. Now I know I have to have 3 to the x is equal to 3 to some power in order to set those powers equal. I can't have 1 over 3 to the fifth. So like I said before, if I have a fraction, I'm probably using a negative exponent. We've talked about those before. If I want a negative exponent, I take the reciprocal of something. So if I take the reciprocal, in other words, bring the 3 to the fifth to the numerator, I can make its power negative. So therefore, x equals negative 5. Okay, here are problems that appear to be a little more difficult. We've got more terms added to the powers, but the properties still should stay the same. I have 3 to the x plus 5 is equal to 9 to the 4x plus 3. Now there's no way I can do this problem unless I have the same base term. Well, luckily, I can say that 9 is the same as 3 squared. So I can get bases of 3's in this case. Except the term on my right, I still have some work to do because I have 3 squared raised to the 4x plus 3. And we've talked about this before. When we have a power raised to a power, we simply go ahead and multiply those powers together. So this is 3 to the 8x plus 6. And now if I have the same base, my two powers must be equal. So I have x plus 5 is equal to 8x plus 6. I can subtract x to both sides. Get 5 equals 7x plus 6. Subtract 6 to both sides. Get 7x equals negative 1. And then divide by 7 to both sides and get negative 1/7 is equal to x. On this side, once again, we see a fraction, so chances are we're going to have a negative exponent. Let's go through and do some of this. I have 4 to the 3x and 1/8. So I want to try to get 4 and 8 to have the same base. Now, the problem is 4 to any power that I know of is not going to equal 8. And 8 to any power that I know of is not going to necessarily equal 4. So I'm going to have to change my base maybe on both of them. And the most likely base I can think of is 4 is 2 squared and 8 is 2 cubed. So let's go ahead and make a base of 2. So what I have now is I have 2 squared raised to the 3x and 1 over 2 cubed. So in this case, I'm going to multiply the two powers together, giving me 2 to the 6x power. And in this case, I need this base to come to the numerator, so I'm going to use a negative exponent. And now I can set the bases the same, or since the bases are the same, I can set the powers equal. So I have 6x equals negative 3. And dividing by 6 to both sides, I get x equals negative 1/2. Now, in this next problem, let's go back. In this next problem, we see we have 27 equals x to the 1/4. The thing you're going to have to be careful of, first of all, is noticing what is raised to a power. Once again, this 3 has an unwritten power of 1 and it's multiplied by x to the 1/4. So in order to get x by itself, I need to remove this 3 from the problem. So I'm going to divide both sides by 3, giving me 9 is equal to x to the 1/4 power. Now the next thing I have to recognize is that x is being raised to a power. It's not being multiplied by a 4th. So I have to somehow undo this power and get x to the first power so I can answer the problem. Now the easiest way to do this, I find, is if I want to make this 1, I could multiply the 4th by the number 4 and that gives me a number 1. But if I want to take and multiply powers, then I'm going to have to raise both sides of my problem to the same power, and that's fine to do. Whatever you do to one side, you have to do to the other, and that's balancing an equation. So we have a new technique in the problem. We want to take and change an exponent. We raise both sides of our equation to a same power. So in this case, I have 1/4 times 4, which is 1, and then I have 9 to the 4th power. And we're just going to leave that as 9 to the 4th rather than make it a huge number. So you've seen lots of different operations with powers and getting same bases and rational exponents. And I'd like you to write your lesson summary and answer those questions below. See you tomorrow.